Chapter 2, Multivariable Optimization. In this chapter, we consider the simplest category of multivariable optimization problems. I am going to discuss unconstrained and constrained optimization problems separately. 2.1 explain unconstrained optimization. As I mentioned before, we are going to discuss two types of problems: unconstrained optimization problems and constrained optimization problem. An unconstrained optimization problem is one where you only have to be concerned with the objective function you are trying to optimize. So objective function, suppose we are going to maximize f, x, y, z equal x plus 2y plus 3z. So this is the objective function. So none of the variables in the objective functions are constrained. These type of problems are called the unconstrained. But constrained optimization, let me write down the same function max fx yz equal x plus 2y plus 3z. Here we should have a constraint such like x squared plus y squared plus z squared equal 3. So you have to consider this second one also. Therefore, this is a constrained multivariate optimization problem. Let me explain unconstrained optimization problems first. This is the example 2.1 in the page number 21 of our textbook. A manufacturer of color TV sets is planning the introduction of two new products, a 19 inches LCD flat panel set with the manufacturer's suggested retail price of $339 and a 21 inches LCD flat panel set with the MSRP of $399. The cost of the company is $195 per 19 inches set and $225 per 21 inches set, plus an additional $400,000 in fixed cost. In the competitive market in which these sets will be sold, the number of sales per year will affect the average selling price. It is estimated that for each type of set, the average selling price drops by 1 cent for each additional unit sold. Furthermore, sales of the 19 inches set will affect sales of the 21 inches set, and vice versa. It is estimated that the average selling price for the 19 inches set will be reduced by an additional 0.3 cents for each 21 inches set sold, and the price for the 21 inches set will decrease by 0.4 cents for each 19 inches set sold. How many units of each type of set should be manufactured? Now, let me summarize this. A factory manufactures color TV of 19 inches and 21 inches. Yes, we do have two types of TVs, 19 inches and 21. Then we do have their cost, $195 per 19 inches and $225 per 21 inches. But they do have the fixed cost $400,000. So then we do have suggest price, $339 per 19, $399 per 21. Then market impact, average price drops by 1 cent for each unit sold. Average price of 19 reduces additional 0.3 cents for each 21 sold. The average price of 21 reduces additional 0.4 cents for each 19 sold. So these are the market impact. Asking how many units of each type should be manufactured. So we are going to follow the 5-step method that we discussed in chapter 1. Step 1, to define the variables, assumptions and objective. So first, variables. So I use S, T to represent the number of 19 and 21 inches TV respectively. Then P average selling price of 19, Q average selling price of 21. C total cost of manufacturer, R revenue from the sale, P profit. Now assumptions. So what are the assumptions? We know selling price for a 19 inches set. Let me write down an equation for this. Simple P we use. I will use simple P. So simple P equal, they have already decided to sell, it is a $339. But they say average price drops by 1 cent for each unit sold. Therefore, 1 cent, 0.01 S is the number of 19 inches sets. And not only that, saying average price of 19 reduces additional 0.3 cents for each 21 sold. Therefore, we have to subtract that also 0.003t. We can write an equation for the Q, which is selling price for 21 inches TV. So similarly, they have decided to sell that 399. Then the average price of 21 reduces additional 0.4 cents for each 19 sold. Therefore, this should be 0.04 S minus 0.01 T. Now go to the R is income. How do we find income? You know, number of TVs sold multiplied by the price for the one TV. So number of 19 inches set, we have S, and cost selling price P. Then plus similarly for the 21 inches QT. Let me write down an equation for the C, which is cost of manufacturer. Yes, we know that is the 400,000, that is the fixed. So 195 for one TV and 19 inches, therefore 195 times S. Then $225 for the 21 inches TV, therefore 225 T. Profit equal P equal income R minus cost C. So here we definitely know S greater than equal 0 and T greater than equal 0. So these are our assumptions. So then objective, what is the objective? Maximize P. So maximize the profit. Step 2 is to select the modeling approach. Suppose we are given a function y equal f x1 xn. This is a function with n variables. A point can be written xn and in the set S. We can get the gradient of the function and set this equal to 0. We can get the partial derivatives of the function, then set them equal to 0, which is partial derivative of f with respect to x1, set this equal to 0, partial derivative of f with respect to x2, set this equal to 0, so on, partial derivative of f with respect to xn, set that equal to 0. So now you see we do have n number of equations and n unknowns. So we can solve this system of the equation and find the unknowns. Step 3 is to formulate the model. Using the standard form chosen in step 2, I can write down the objective function p equal r minus c. So you can plug the values r and c. After plugging the numbers, we can get the objective function p equal 339 minus and this plus this part plus this part. So this is our objective function. So let me write down this familiar form in familiar form. So what I do, I use a y equal p, the profit, and x1 equal s and x2 equal t. So then I can write down the function y equal f x1 comma x2. So this is our function with two variables. So we do have two unknowns x1 and x2. So we should have two equations. Yes, let me write down this first. This is over the set. We should know the s. S should be x1, x2, and we know x1 greater than equals 0 and x2 greater than equals 0. So this is our set. Step 4 is to solve the problem. We have the function f x1 x2. It is the function with two variables. So what we should do, by step 2, we get the partial derivative of the function with respect to x1, set this equal to 0. So let me write down the partial derivative of the function, this 0.02 x1 minus 0.007 x2 equals 0. Then partial derivative of x with respect to x2, this 174 minus 0.007 x1 minus 0.02 x2 equals 0. So now we do have two equations and two unknowns x1 and x2. So we can solve these two equations for x1 and x2. So you can get x1 equal 554,000 divided by 117, approximately 4,735. x2 824,000 divided by 117, approximately 7,043. Now we need to confirm these two values x1 and x2 give the maximum of f. So let me explain this. Suppose f1 equal partial derivative of f with respect to x1 and f2 equal partial derivative of f with respect to x2. Then I get the second part of this. I write down f11. It means I get the derivative of f1 with respect to x1. Here also similar, I write down f22. It means get the partial derivative of f2 with respect to x2. f12, that means get the partial derivative of f1 with respect to x2. f21 should be partial derivative of f2 with respect to x1. D equal f11 f22 minus a second power of f12. Okay, find the d first. Then first one, if d greater than 0 and f11 greater than 0, x1 x2 is a minimum. Second, d greater than 0 and a less than 0, then x1 x2 is a maximum. That is the should be local minimum, local maximum, but I write down this way: d less than 0, then AB is a saddle point. Last one, if d equals 0, then no conclusion. So according to above steps, we know f1 equal 144 minus 0.02 x1 minus 0.007 x2. So then let me find f11. F11 mean derivative, it mean derivative of f1 with respect to x1. So this equal negative 0.02. Then f21 12 equal 0.007. F2 equal 174 minus 0.007 x1 minus 0.02 x2. We can write F22 0.02, F21 0.07. D equal F11 negative 0.02, then F22 negative 0.02 minus F12 negative 0.007 to power 2. So D equal 0.00031, which is greater than 0. So we know F11 equal negative 0.02, which is less than 0. So then go to the second one. It's a D greater than 0. Yes, it is greater than 0. F11 less than 0. Yes, it is less than 0. Then maximum value. Therefore, we can say x1 equal 4735 and x2 equals 7.7043 gives the maximum value. Give the maximum value of f. Then find the maximum. F x1, x2, we know this one. Find x1 equal 4735, x2 equal 7043. So then you will get y equal 21,592,000 divided by 39. This equal 553,641. So this is the maximum value. That means this is the maximum profit. The final step, step 5, is to answer the question. You can write the company can maximize profits by manufacturing 4,735 of the 19 inches sets and 7,043 of the 21 inches set, resulting in a net profit of $553,641. Okay, now let me explain how to use the WX Maxima here, WX Maxima package to solve this optimization problem. So this is the objective function. So let me run this one. So you will get the function very clearly here. So once we have an objective function, we should get the derivative, partial derivative with respect to x1 and x2. So these two steps do the partial derivatives with respect to x1 and x2 respectively. So see, this is the partial derivative with respect to x1, and next one, this is the partial derivative with respect to x2. Then next step, to set these two equals 0 and solve for x1 and x2. So this is the command. You see that dy dx1 equals 0, dy dx2 equals 0, and for the for the x1 and x2, so just run it, then you will get the x1 value and x2 values over here. So we can use this package to solve this problem very easily. Then how do we find the maximum value of x? Yes, here run this command s comma y, then you will find the maximum value of f, that is the maximum profit. Okay, now let me just check the graph, the plot of this problem. So let me run this one. Okay, this is the plot. So you see this is a 3D plot. So this is the graph of profit versus production levels x1 and x2. So let me show you, make this white background. So then you will see here x1 and x2, and this is the profit.